node to the end of the list. So it goes all the way and adds something to the end. Now, the list is going to get longer and longer and longer and longer. So if the first few times you do an add, it's very fast, but after it's longer and longer and longer, it takes more time. It's going to go all the way down the nodes. Let's just take a okay. Okay, so we got the linked list, and we always add to the very end. Your job is to add another pointer called the tail to the class. So remember we were talking about what would be faster to add to the beginning or add to the end. And we found out that it would be faster to add to the beginning because you don't have to go all the way down to the end. So if you have a list with lots of nodes like this, and of course the last one has got to point to 0, and then here's the head points to the first one. If you want to add to the end, you got to go and then finally put it in there and fix up your pointers. We'll call this head. Now it would be faster to just add it here, but let's say you want to add it at the end. It would be unfair to let the new person always go to the head of line. That would be butting in. So we're going to go while runner equals runner next, something like that. That'll give us down to the end. But then, of course, then our runner goes all the way down to the end, and we got no, so we got to keep track of our previous. It's just a pain. So what we'll do instead is we'll create a new thing in our a new pointer in our class, and we'll call it tail. And tail will always point to the very last item. Okay? You got to make sure it doesn't point to null. The last item can point to null. The last item always should really point to null, but tail is going to point to this one. Now, when we add a new item, instead of having to go down to the end, we can just go right down to the end with tail and stick it on the end and then make tail point to it. Okay? So this is a performance improvement, a tremendous performance improvement. So your job is to add another pointer called a tail to the class. A tail is like the head, except for the tail points to the last item. And so then, now when you modify add, so when add gets done, instead of going while new, you just go to tail, insert the new item and tail. If you can fix up these pointers right, or else you'll get an endless loop, or something will mess up. So you got to be careful about the pointers. But after that's done, okay, when that's done, modify add to the new code. New add will be added very quickly to the end of the list by using the tail pointer. There's no traversals required. Make sure that when you update the tail to add the new node, so it'll work for multiple calls. Because I'm gonna ask you, well, what if you add several nodes and they should all work? So test the program to make sure it's worked. So let's just take a look at that code, the starter code. That lab is in, let's see, that's publisher code, publisher source, and down here in chapter 17, modified, and I'm going to set this code here. Oh, yeah, right here, thanks. Okay. Okay, so this is, So we've got our list node that looks very similar. Now here's what's, this is a little bit more complicated than the previous example. This actually has several things it's trying to do at once here. It says we got class number list, and in number list it's kind of embedding the structure within a class here. So we've seen this before. The list node structure has a value and then a pointer to the next. And in order to create a brand new list node, it has this constructor inside the struct. And you've seen constructors inside a class, but here's a constructor inside a struct, and the struct is inside the class. A little bit complicated, but you've seen it separately before. And so this struct has a constructor, list node has a constructor. If you give it a double, that'll put the value into the value portion of the list node. And if you give it a pointer to a list node, and it will put that in here. Now do you remember, what does it mean if I have a function and I set one of the parameters like this? Remember what this does?
Default parameter.
It's a default parameter. So there's two ways I can call this constructor. I can call it with just one parameter with the value. If I do that, it'll automatically put null into the next one. So if I just do a new list node and give it a number, it will put the number in there and put a null pointer into here. And then here's the head. What you're going to add is tail. So it'll add a tail to here. Let's see what it does now. So when you create a new number list, and this whole thing is a linked list, inside it describes what one node looks like, but it'll have on head, it'll have node after node after node after node. And so when you create a new number list, here's the number list constructor, class number list matches this constructor. When you start out with a new number list, all it has to do is set the head to null. There's nothing on there. And when you want to delete the number list, you're going to have to call this destructor, which has a fair amount of work to do, because the destructor has to go and delete every single one of these nodes in a loop. So deleting the list takes a long time. So here we'll add a new node, and this currently, I think, runs down the list to the end, and remove. This one searches the list for that number. It will do something like while runner, if the value that you're looking for is the number, keep going. And then you'll find a node, and then you can delete the node. So this, we'll see this code here later. This says to add a number to the linked list, and this says remove the number, so that has to find it and then delete it. Let's take a look at what some of this stuff does. And here's the kind of slow and inefficient add. Add says, I want you to add a node to the list that will contain this number. It's got to check. This may be the very, very first time you've added a node to the list. And if it's the very first time you've added a node to the list, that head will be null, and then you have to create a new list node, and you'll put the number in it, and you'll set the head to this one. And that's the end of the code. Okay? Just a couple lines of code. What that says is create a new one of these things, put the number in here, say it's the number 75, and then put the head, and point the head to this. And what else does it do? When does it, is it making a mistake here?
No, it's the default value is being put in.
So right, it works because when we say, this is a constructor, so list node, we'll call it a constructor, it'll have the value of the number in it, and because the second parameter of the constructor, which we just saw, is calling this, here's the constructor, because the second one is null, it will automatically put a null in for the second one, and it'll set next equal to null, so it will do this. So it does the right thing. And that's what happens when you put in your first item. And then what does it do if it's not the first item? Well, if it's not empty, it's already got something there. So now use the node pointer to traverse the list. So, and I use the word runner. I like runner because I like the idea of the thing running down the list. But they're calling it node pointer. So they're saying set this pointer to a list node called node pointer to head. And that was my example runner. And then while, now notice notice it says, while node pointer next is not equal null. No. You can do it this way. But I would just say, while node pointer, and not, I wouldn't have all that. But, you know. So that makes it easier to understand what it's doing. If you haven't done this very much, that might be very helpful. I've got the node pointer. I'm checking to see if the next is not equal null, and that works fine. However, the way I did it on the board is just, you know, just say, if you, I could set head to runner, while runner, just keep going. Okay? So we go down, and what this is doing is it's running down the list until it, actually this is kind of interesting. You see what this is doing different? This is actually kind of interesting. He's going 2 pointers down. So when I did this, I said while runner. What he's doing is take runner and look at the thing after the runner. So what they're doing is they're saying, take this, the node pointer, follow the node pointer down, and follow that down and see if that is 0. So it's actually doing a double indirect. This is a kind of a nice way of tracing the list down, because he wants to seek to get to the end of the list that has the 0 on it, but he wants to keep track of the pointer to the thing. So he says, set the node pointer to head, which is going to then point to this, and then check to see if what the node pointer points to and what it points to in next is 0. See what it's doing? It's actually doing a double indirect. Follow the node pointer down to the next, and follow that down to see if it's null. And if it's not null, then keep going. And keep going until you get to the very end. And then when you get to the end, make a new list pointer, put the number in there, and set the next. What this will do is it creates a new list pointer here, and then it says make a new one, put the number in here. I'll say the number is 999, and then it automatically puts the 0 in there because it's the default parameter, and then it takes this end pointer, which is down here, and it says, well, here's what it's doing. By now, end pointer is pointing, one end pointer is now pointing to here. Okay, end pointer is pointing to the one before it. So end pointer is pointing here, and follow the next, which is this, and take this, and make this, point to that. This, the thing is with pointers is there's not a lot of code here. It's fairly meticulous, and it's following a pointer, it's grabbing the thing, and it's putting the pointer in there. On the exam, what I do is I give you something like 8 lines of code, just very similar to the code that we've just seen. And I say, given this code, show me the picture of how it's setting up these pointers. Okay, so that adds one. If this is kind of short display, we kind of have this on the board. If we wanted to start at the head, we would set the node pointer or the runner to the head. And now here, see how they're using the while node pointer? That's the same syntax that I had. While the thing has a valid pointer, it's not null. They just print out the value and go on to the next one. So that you've seen before with that previous example. The destructor is actually got to do a fair amount of work, because if I have a linked list of several thousand of these, I am going to have to, remember how new goes with delete. So if I don't do a delete, I'm going to have a numbering. For every new should be followed by a delete. So if I'm going to get rid of my entire list, be kind of careful. I'm going to keep track of the node to be deleted. What he does is, let's see, he says take the node pointer, set it to head, and then, oh, he's creating a brand new list of garbage. So he's saying, say garbage is a pointer to a list node. So garbage. And set that to node pointer, and that's pointing to the head, so it's doing that. And it says move on to the next node if any. Then here's why it's doing this. It's setting the garbage pointer here because I am going to delete every node on my list, and when I delete it, the pointer, everything beyond is going to be inaccessible, right? If I were to, say, delete the first item on the list and lost track of the pointer, then all of this would be a memory leak. So he's saying if you want to delete this first node, set garbage to point to the first node, and then delete what garbage points to. And then I'll still have the pointer to the next thing. So he says, set garbage equal to the node pointer, then set the node pointer to what follows next. So he says, set garbage is going to point to this, and then I'm going to move my node pointer to the next one, then I'm going to delete that, then I'm going to set garbage to this and delete that after I move my pointer to that. So you can't delete a structure. As soon as you delete a structure, you better not use a pointer to it. If you have a pointer to a structure and you've deleted the structure and you still try to use the pointer, you don't know what you're dealing with. So, and this is how it would get called here. It adds a few numbers, it makes a new list, adds a few numbers to a list, and displays the list. So your job is on lab 17 to do a couple things. You want to add a tail in here, so that would go right here. You got a list head pointer. And then you could add a tail. And now we're going to modify add, because now what add is doing is it's going all the way down to the end of the list to find the end, but you already have it. You've got tail. You got to be a little careful here with tail, though, because if I add a new node in the constructor, you better make sure tail points to the one at the end. Okay, so in the constructor, you're going to have to modify the constructor too, because right now tail won't point to anything. So does that make sense on the linked lists so far? Okay, so we've got a node containing the data in the pointer. You should always initialize your head to null when you first create your head, because otherwise you might start using it and it's pointing to garbage and it will just go off and do nonsense. C++, of course, just now, this is interesting. I like to have my pointers as the first thing. And I'll tell you why. Remember when we looked at chapter 15, we were looking at virtual functions and how you can, in this case, and this is all we're going to do in chapter 17, but in chapter 17, the linked list pointed to things that were all the exact same things, okay? So they were all the same. However, in polymorphism, you might want to have a list of things that are not all the same things. For example, if you had a list of objects that you wanted to draw on the screen, and this was a square, and this was a circle, and this was a line, and this was a line, and this was a letter. You might have, and this is how drawing lists works. When people write games, they have to have a list of all the things that appear on the screen, and then they go down the list and then they draw these things really fast. A lot of times when you bring up Windows, you'll notice how it draws all the icons all over again really, really fast. It's going down a linked list of all the things that are appearing on the screen, and it's drawing them. So it might have an icon, or a window, or a background, or something else. And this, what it points to, it'll do something like this. It'll set the runner to the head, and then it'll say something like, while the runner, and as while you still have more objects, you'll do something like runner dot draw. Okay? And so runner can point to a large number of different things. It'll say, it might say runner dot draw. So runner is runner would be like a pointer to a displayable object, and as you go down the list, you would draw each one, and you would call a different function depending on what it was, line, etc. So that kind of gets into polymorphism. So in order to handle the case where each item is a different size, it kind of makes sense to have the pointer at the top, because then the pointer is always at the same place on all the nodes, and so that's why I tend to put my pointers at the top. But we've got it here, and so we've got that, so we've got the data and the next, and we kind of saw this empty list, etc. In operations, we can add a node at the end. That means you have to transfer all the way down, otherwise at the beginning it's a lot quicker. So you should be able to do these things as something for the last exam. The last exam has 4 parts, and the first part is going to be enabled now. So if I look here on assignments, let's see if I can make it a little smaller. Okay, so the exam 3, this in class, I made this available for someone who was taking it a week early, but we're not going to do that. So what I want to do is make sure that I enable this. I'm going to enable the at-home portion now, and that will be, what is today? Today is just, this is going to be available from May 5th to next week. And that is going to be May 12th, right?
Mm-hmm.
And that will be, okay, and that has 2 attempts. All right, so I'll make this available here. And then the other one, which is great. Now, one thing is, I have a Tuesday, Thursday class, and some people have been either sick or missing, and they asked if they could take it on Saturday to give them 2 days. So there might be some guests in on Saturday. And this one I'm going to take off until next time. So. So just to make sure that we could maybe go there. So, it's going to come here in a minute. No,
Yeah.
brother.
40
Okay,
minutes.
I want it to be right now. I just want to make sure everything's in place and working. So the at-home portion, put it right now at 12:20. Because I really hate a week to go by and find out that I didn't think, and I did that once, where
We
there's
did
a
it
point,
too.
where it's point of thing, and then I didn't have it up and running, and I came in and they said, well, oh shoot, I had it for like 1912 instead of 2012. Okay, so there it is, the at-home part. It has, it's the first of 4 parts, and it's a, this is kind of comprehensive. Here's a good one, a search. What kind of search uses a loop to sequentially step through an array? Binary, global, binary. I would have called this a linear search.
It's on it, it's the bottom.
Is linear there? Okay, yeah, linear's there. So, and so you can see this is kind of going back to, I think, chapter 9 is roughly where we did searching and sorting. So there, let me just see how many are on here. There's a whole pile, there's 80, so that's gonna take a while to do.
Oh.
So, move it wrong. But you got a week. So have that done by, that's kind of a review for the next week. And then there'll be an in-class portion, which is similar to this. And then there will be a written portion which covers, it'll emphasize the last few chapters, 12, 13, 14. Let me just, I'm going to put, there's another notice that I'm going to put up for you in a minute, but I want to show it. I have this up here. Here's my, I'm going to post this in a little bit, but I know we got 1 week left, so you're thinking, oh, thank goodness. But here's some tips for the last week, okay? Okay, tips for closing out the course, and I'll post this on our website in a minute. The tips for last week are on lab 12 or 13. I don't know if you've done those or not, or finished. Remember, the labs aren't completely due until you're tested on them. You'll be testing them on in a week. These are mostly for review. Lab 12 was to do the testing of the password, to make sure the password had all the right characters and letters in it, and the right length. So that's, and then the string one was to count the number of letters in a file. So if you get a file full of letters, you should come up with a little histogram of all the letters. A has this many letters, etc. So those I hope were mostly review because you've done file I/O before, and what's new on Lab 12 is you can pick whether you want to use a C string or a string class. Okay, Lab 14 is recursion. I know a lot of you were working on recursion, and you're supposed to annotate a recursive function and show me that you understand how it works. A good way to annotate a recursive function is to show that you can see every enter call, every call that's entered. So if I have a recursive function like this, if I have a recursive function like this, I might want it, I kind of like doing this. I'm going to say, I'm going to do a static counter. And I can, this static counter, remember there's only one of these for the function. And then when I enter the function, I might want to say I'm entering the function. And if I have some parameters, say P1, P2, what's very helpful is saying an entering function, show what P1 is, show what P2 is, and show what the count is, okay, when you enter. And then you're going to, at some point, call yourself again. And then at the very end, or at various places, you're going to return. Okay? Before you do your return, you should have some output that says exit. And your exit can also have your counter. Oh, I didn't put counter in here, so yeah, here's counter. You can have a counter for your exit. And then perhaps the parameters that you were called with, and perhaps the value that you produce. For example, if you're calling the function again, and the function has a value that it returns, then you can set the output value to here, and then put what the output is. Okay? So every time you enter your recursive function, you should produce a statement that shows, hey, I'm entering it, and every time you leave it, you do a statement that shows that you're leaving it with some information. Then when you run it and look at it and think about it and go back and look at the code, you go, okay, I'm coming in here, and I'm going. Now some of these are a little complicated because you might exit in several places. And you gotta cover all your exits. Sometimes it might be turned. In fact, in Fibonacci, you call yourself twice. So you enter once, but then you call yourself twice, and then each one of those has to exit. And you can match the entrances to the exits if you have these in here. Okay. So that is recursion. Now in Lab 15, what this one does is, we were talking about virtual functions where you can have a class and the class is designed to be inherited. So you should be able to do this. If I have a class A and I have a class B, I can make a class C. I can make a class C that extends A. Okay? What that means is I've got A over here, I've got B over here, and now C, here's C, it extends A, so I'm going to have A, plus I'm going to have whatever extra things I have on C. Okay? So C is going to be a combination of the old A plus the new C, and it's going to be this structure here. There's two ways. This is called inheritance. This is aggregation by inheritance. But there's another way of doing that, and that is I can say class C, and then here I can say class A. Okay? And what this is this composition. This is composition. And this is in, I think, chapter 15. This is composition, and this is inheritance. And they, in some ways, they're pretty similar, because here says, I'm defining a new class, a class C, it extends A, and so it takes everything that A has and it adds C onto it. What this does is this says, I have a class C, here's C, and it includes an A. Okay? So this, which is composition says C includes an A, is very similar to inheritance, which says that C is an extension of what A is. Very similar, slightly different. What's slightly different is this. If I look at class C, here's class C. If I look at class C, I can see all of the functions for A and all the functions for C. They're visible to me, because if there's anything public, if class A, for example, has anything that says public, and I inherit class, and I inherit everything from A into C, then I'll be able to call all the A functions and call all the new C functions. That's inheritance. But if I have composition and I bury A, particularly if I put A in my private area, then that's hidden from me, and I can't see it. So in the Strustrip book, he says, and people, you see endless debates about this. Should I use inheritance or should I use composition? And there's, I guess nerds just spend till 4 in the morning arguing. It's one of those arguments that will never, like paper or plastic, they'll never finish the argument. But in general, composition is a little safer because it keeps A's data, it gives you more control over A's data, it keeps it a little bit more private. And then you let C handle all access to whatever is going on in A through setter and getters that are public in C. And it just keeps A a little bit more tightly controlled, where this one, it kind of opens it up. So you should be able to at least remember the syntax for inheritance and composition, a little bit of the differences between those. And in what Lab 15 does is it says that I'm going to give you a class, and the class is able to encrypt files. There's a pure virtual function called transform, and it takes every single letter in the file and just tweaks it a little bit. It adds one to it. It's a pure virtual function so that you have to implement it in your derived class. Remember, if you have a virtual function, then you can implement it in a derived class. So you can implement it in the derived class a little bit differently. You'll implement a virtual function in derived class. Okay, in 17, we kind of went over 17. That's linked lists. We're only going to cover about the first third of chapter 17. And we did that. It's on linked list of the first 10 pages. And then exam 3 is up there now. Trying to think of this. So what we're, next week, on Saturday, we don't necessarily need from 9:30 to 12, or 9 to 12:30 to do this test. Okay? However, I think, yeah, but that's what I said last time. But some people were done there. Okay. So I think what I'll do next time on Saturday is maybe for the first half hour, 45 minutes, entertain any questions, go over any issue. I may have the test in front of me and just kind of, I'm not going to tell you answers so you can be great, but I'm going to just, maybe kind of, get you thinking a little bit on some of the things in the test, and then hand it out. And we may have some guests, because on the Tuesday, Thursday class, some people might be here from the Tuesday, Thursday class. But, and then there'll be the written portion and 2 things on Blackboard. Okay.
So, will we get kicked out of that lab?
Well, here's the thing, is the written part takes a while to do, okay? And let's see, we might get kicked out. So what we got to do is when we go in, I think what I'll do is when we go in,